Good morning to all. Today our topic is resistance switching. Yesterday we have seen different expressions for restriking voltage, rate of rise of restriking voltage, maximum value for restriking voltage, maximum value for rate of rise of restriking voltage, and average value for rate of rise of restriking voltage. Now we already know that circuit breakers are protective devices which are used in the power system. So to interrupt the fault under abnormal condition. Under normal operating condition, they can be used as switches. Now, so whenever circuit breaker contacts are open, okay, so you can see a circuit breaker here in this circuit. So whenever circuit breaker contacts are open, we already know that arc will be struck in between the contacts. Okay, so arc will be consisting of ionized particles. Okay, and circuit breaker contacts are actually placed within an insulating medium. It can be air, oil, or SF6, or it can be vacuum. Okay, different insulating mediums also we have already discussed. Okay, so now when arc is struck between the contacts at some current zero of the arc is interrupted. Okay, so when arc is interrupted, the voltage that appears across the circuit breaker contacts is known as restriking voltage. Okay, now if the magnitude of this restriking voltage is very high, then this restriking voltage may restrike the arc. Means even though arc has been extinguished at some current zero across the circuit breaker contacts, arc may restrike due to this restriking voltage or due to the rate of rise of restriking voltage. Means if the rate of rise of restriking voltage is higher than the rate of rise of dielectric strength between the contacts, okay, so what will happen? The arc will restrike. Okay, so to reduce the restriking voltage, okay, and to reduce the rate of rise of restriking voltage and the severity of the transient oscillations which occur in the circuit, okay, a resistance is connected. You can see a resistor here. A resistance is connected across the contacts of the circuit breaker. This is known as resistance switching. Okay, so what is meant by resistance switching? To reduce the restriking voltage, rate of rise of restriking voltage, and severity of the transient oscillations, okay, a resistance is connected across the contacts of the circuit breaker. This is known as resistance switching. And if you observe here, okay, if you observe here, this resistor is connected across the contacts of the circuit breaker, means we can say it is across the arc. If arc is struck between the contacts of the circuit breaker, okay, it is this resistance will be parallel to the arc. It is across the arc, we can say. Okay, so part of the arc current will flow through the resistance. Okay, when arc is struck, okay, between the contacts of the circuit breaker. Okay, so whenever fault occurs, if arc is struck between the contacts of the circuit breaker, then part of the arc current will flow through the resistance, resulting in decrease in the arc current. Okay, since some part of the arc current is flowing through this resistor which is connected in parallel to it, therefore what will happen is arc current will be reduced. Some may not completely, but part of it will be reduced. Okay, so when arc current is reduced, already circuit breaker contacts are placed within an insulating medium, dielectric medium. Okay, so because of the flow of some part of arc current in this resistor, what will happen is deionization of the arc path will take place. Okay, hence what will happen is the arc resistance will increase. Okay, so whenever we connect a resistor across the contacts of the circuit breaker, and when arc is struck across the contacts of the circuit breaker, whenever fault occurs, when the circuit breaker contacts are moving apart, okay, some of the arc current will start to flow through this resistor. Okay, so what will happen is this will cause the increase in the deionization of the arc path and increase in the resistance of the arc. Okay, so as this process continues, the current through this shunt resistor will increase and arc current will decrease. Okay, the current through the resistor will increase and the current in the arc will decrease. So due to the decrease in the arc current, the restriking voltage and rate of rise of restriking voltage will be reduced. Okay, so of course our current has reduced, but at some current zero arc will be interrupted, arc will extinguish at some current zero. Okay, so when arc is extinguished, as soon as arc is extinguished, what will happen? A voltage will appear across the circuit breaker contacts. That is the restriking voltage. So the voltage across the voltage across the circuit breaker contacts, that is restriking voltage, its magnitude will be reduced, and the rate of rise of restriking voltage will also be reduced because of this resistance which is connected across the circuit breaker contacts. Okay, so the resistance switching is helpful in switching out capacitive currents or low inductive currents. Okay, so resistance switching is usually used to interrupt the capacitive currents of the circuit as well as low inductive currents of the circuit. Okay, so resistance may be automatically switched in with the help of spare gaps. Okay, so you know. Okay, so spare gaps means so two spheres with a gap, two spheres are connected in between within the circuit. Okay, so you just connect a resistor across the sphere gap. So you have already seen in the case of lightning resistors, so how the sphere gap will look like. Okay, so simply contact sphere gap means it's across the contact gap. That's all, nothing else. The analysis of resistance switching can be made to find out the critical value of the shunt resistance. So what should be the value of this resistor can be, we can determine that value. Okay, in order to damp the transient oscillations. Okay, this resistance will damp the transient oscillations which occur in the circuit. Okay, because of this R. Okay, so what is the magnitude of that resistor? We can calculate. We can do some analysis to determine the resistance value. Okay, so we may not be able to exactly determine the exact value, but we can do some analysis to determine the resistance value. You just carefully observe this equivalent circuit in which some fault current, some short circuit fault current has occurred. Okay, so let us do some analysis to determine the value of this resistance. Okay, so you just observe this circuit carefully. Let us assume the system voltage is V. Sorry, E. I have written here E. V or E, it doesn't matter. Here I have written E, so let us assume E. Okay, and so this is the equivalent circuit of the system in which some short circuit fault has occurred. Okay, so let us assume the voltage across the capacitor is VC and current through the capacitor is IC and current through the inductor is I, and voltage current through this resistor, shunt resistor is IR. Okay, and we already know, if you remember the previous concepts that we have already discussed, whatever voltage that is impressed across the capacitor when the circuit breaker contacts are open, okay, the voltage will be, means when the arc is extinguished, this voltage will be impressed across the circuit breaker contacts, okay, after extinguishing of the arc. Okay, so now let us derive some equations. Okay, so you people better draw this circuit. We have to derive something. So all of you start writing in your notes now. As soon as you complete to draw this circuit, inform me. You take 1 minute, don't take more than a minute. Make it fast. As soon as you complete, type C. Today, if possible, I will check your notebooks. Draw with free hand. Make it fast. In the next class, we are going to solve some problems. So make sure you have calculators and all with you. Did you complete? Why you people take much more time? Did you complete? Are you people writing or not? Did you draw the circuit?
Yes, ma'am.
Okay then. Okay, completed. Okay, now if you see carefully here, this is our system voltage. You can represent the loop equation for this. Equation is E is equal to the voltage across inductor plus voltage across the capacitor. Okay, so this is it. So voltage equation is what? E is equal to L into di by dt plus 1 by C integral of IC dt. This is very much familiar to you people. Okay, okay, where I is nothing but IR plus IC. Okay, so this is I. I is equal to what? IR plus IC. It's short circuited here. So IR plus IC is our I value. Okay, so you can substitute I value here. What is IR plus IC? So substitute IR plus IC in the above equation and you just further simplify it. You can rearrange the terms. So L into d by dt of IC, L into di by dt of IC plus L into dr by dt plus what is 1 by C integral IC dt? It is the voltage across the capacitor. Voltage across the capacitor is nothing but Vc. So you can rewrite and you consider it as equation number 1. Okay. And what is IC? IC is the current across the capacitor. The current capacitor current can be written in terms of charge, that is d by dt of Q. So what is Q? Q is nothing but CV. Q is equal to CV. You already know that. Okay. So instead of Q, I'm writing d by dt of C into Vc. IC is equal to d by dt of C into Vc. As soon as you complete, just type C. As soon as you complete this slide, inform me. Completed? Just type CM if you complete. Okay, very good. Okay, so you know what is IC. So just differentiate it with respect to dt. So d by dt of IC is C into d square Vc by dt square you will get. Okay, consider it as equation number 2. Okay, and what is IR? IR is voltage across the circuit breaker contacts by resistance R value. Okay, voltage across the circuit breaker contacts is nothing but voltage across the capacitor. So IR is equal to VC by R. So again differentiate IR by dt. So d by dt of IR is d by dt of VC by R. You will get 1 by R into d by dt of VC. So d by dt of IR is 1 by R into d by dt of VC. Now you have got an expression for d by dt of IC and d by dt of dt. I'm sorry, d by dt of IR. So if you see in your previous equation number 1, you have these terms d by dt of IC and d by dt of IR is there. So substitute equation number 2 and 3 in 1. Okay. So you just substitute it, you will get L into C into d square Vc by dt square plus L into 1 by R d by dt of Vc plus Vc is equal to d. Okay. Now you can take the Laplace transformation for this equation. If you take the Laplace transform for this equation, you will get LC s square Vcs plus 1 L by R. For d by dt of Vc, you will get s into Vc of s. For d square by dt square of Vc, you will get s square into Vc of s. Vc, for Vc, you will get just Vc of s. So E by s. Okay. So here E is a constant, that's all. Okay, if you complete, inform me. Okay, completed, very good. Now, so you just take Vc of s common in the above equation, you will get Vc of s into Lc s square plus L by Rs plus 1 equal to E by s. And again, after taking Vc of s common, you again take Lc common. Okay, if you take Lc common, you will get Vc of s into Lc into s square plus 1 by Rcs plus 1 by Lc equal to E by s. Okay, so you have got some expression here. You determine Vc of s. Vc of s will be what? E by s into 1 by Lc into s square plus 1 by Rc of s plus 1 by Lc. So you can rewrite those terms as Vc of s is equal to E by LCS s square into s square plus 1 by Rcs plus 1 by Lc. Okay. Okay. So for you have got some expressions here. So you just write it down. These three equations. So for no transient oscillations, all the roots of the equation should be real. Okay, if one root is 0, then S means that is S equal to 0, then the equation will be real. For the other two roots to be real, the roots of the quadratic equation in the denominator should be real. Okay, so for that, let us determine the roots of the quadratic equation in the denominator. So just take the quadratic equation of the denominator. I have taken it. Okay, s square plus 1 by rc of s plus 1 by lc. Just consider the quadratic equation in the denominator and let us simplify it to see whether it's real or not. If you complete this, inform me. No need to write this theoretical content, you write only the equations. If you want to write anything, you just write on the quadratic equation in the denominator. Quadratic equation in the denominator. Just write down this, that's all. As soon as you complete, inform. Okay, very good. Now we have considered the quadratic equation in the denominator. Let us determine the roots for that quadratic equation. Okay, so S1 S2 is equal to minus 1 by RC plus or minus root 1 by RC whole square minus 4AB. And that is 4 into 1 into 1 by LC by 2A. 2 1. Okay, so you just divide the numerator by 2, you will get 1 by minus 1 by 2 RC plus or minus 1 by 2 root 1 by RC whole square minus 4 by LC. Okay, this is what you will get. Okay, I have sent this 1 by 2 into this root. Okay, so and I send this 1 by 2 into, okay, no need to even, okay, I have sent it inside the root. Okay, so I have got my new expression is minus 1 by 2 RC plus or minus root of 1 by 2 RC whole square minus 1 by LC. Okay, this 4 will be cancelled when this 2 goes inside the root. Okay, so now consider this expression within this root. So this is a okay. So when you consider it and assume it is greater than or equal to 0. Okay, for the roots to be real, the expression within this root, okay, so must be greater than or equal to 0 for these roots S1 and S2 to be real. Okay, so you just consider this expression within this root 1 by 2 RC whole square minus 1 by LC greater than 0. Okay, and in order to simplify it further, you send this 1 by LC to the right hand side. Okay, okay, I will complete this, only 2 more steps are there. After that you can write it down. Where am I? Okay, yeah, so after sending it to the right side, okay, so you just expand the equations. So you will get 4 by LC into less than equal to 1 by R square C square. Okay, from the above expression. So where you just rearrange the terms, so R square will be less than or equal to LC by 4C square. R will be less than or equal to 1 by 2 root L by C. Okay. So C will be C square is there. They will be cancelled. Okay, I need not tell you. You are not kids. Okay, so you have got some expression for R resistance which is connected across the R is what? R is the resistance conducted across the circuit breaker contacts. So you have got some expression for R. R is less than or equal to 1 by 2 root LC. So the transient oscillations that occur in the system in which this resistor is connected across the circuit breakers, okay, so for different values of R. So let us see how the transient oscillations will vary. So when R is infinity, okay, so the oscillations, you can see oscillations are severe. Okay, so when R is infinity, oscillations. Okay, first of all, you people complete this slide. Complete this slide. Okay, yeah. People come. Where is it? For you, it has changed. For me, it didn't change. Oh, you complete this slide and inform me. Later on, we will discuss about those waveforms. If you complete, inform me. So in the next slide, actually, I have means I have squared these denominator terms. So 4R square C square. So 4 I have sent it to the other side. That is 4 by LC in the next slide. If you remember, 4 by LC is less than or equal to 1 by R square C square. I have written in the next slide. If you complete, inform so that I will show you the next slide. Completed? Okay then. Okay, you just continue it. So for the see 2, it was 1 by RC whole square was there. So 2 square I have sent it here. That is 4 by LC less than or equal to 1 by R square C square. Okay, you just write down these 3 equations so that I will explain about these waveforms. Okay. So if the value of the resistance connected across the contacts of the circuit breaker is equal to or less than, okay, it is equal to or less than 1 by 2 root LC, there will be no transient oscillations. Okay, so there will be no transient oscillations for the R value less than or equal to 1 by 2 root L by C. Now, if R is greater than 1 by 2 root LC, there will be oscillations. Okay, so if R is equal to 1 by 2 root LC, okay, it will be the resistance value will be known as critical resistance. Okay, the resistance of the means the value of the resistance, you will call it as critical resistance. If R is infinity, there will be many oscillations will be there. Okay, if you observe, this is the arc voltage I am showing you. This is the arc voltage. You know, when at some current zero, when arc is interrupted, okay, arc voltage across the circuit breaker contacts will start to, means the restriking voltage that appears across the circuit breaker contacts is an transient voltage which will have oscillations. If you remember, if you have attended my previous classes, okay, so if you observe the lower image here below this line, okay, so this is one half cycle, this is another half cycle. You can see at some current zero, the arc has been interrupted. Immediately transient oscillations will occur in the voltage. Means restriking voltage is nothing but a transient voltage, you can say. So when if R is infinity, the R which is connected across circuit breaker contacts, there will be more oscillations will be there. Later on it will settle down to the normal frequency voltage, that is known as recovery voltage. Okay, so if R is greater than, oscillations will be a bit less, greater than 1 by 2 root L by C, a bit less when compared to R tends to infinity. Okay, when R is less than 1 by 2 root L by C, then oscillations are completely damped. Okay, no oscillations will be there. Okay, so you people can draw this. If people draw these three waveforms, if you complete this slide, inform, you can draw these waveforms. If you complete this slide, inform me. I hope you are able to see. I'm expanding a bit. This is how, this is, I can't expand beyond this. If you complete, inform me.